Now today we'll spend next 1 hour on the SMR process using natural gas. Natural gas is mainly methane, almost 96% we saw yesterday. And as of now today, almost 75% of hydrogen production is via natural gas, using natural gas. In countries like China, they use a lot of coal, but in India we are mostly using natural gas. Coal is more used for power production. Electrolysis at the moment 5%, 4-5%, but it's absolutely on rise because of its zero carbon emission. So in process design, if you remember from your courses, does everybody know about onion model? In process design, you normally start with the reactive system, and you go with the separation next level, and then you think about heat integration, and finally whatever heat balance is there, you either cool the remaining heat via utility cooling or so, right? So we'll start with the first step, reactive system, reaction chemistry. So there are three major, let's say, reaction in this SMR process. The first one is steam methane reforming. So CH4 and a lot of steam you put in, it will be converted to CO and hydrogen. Apart from this, there is also a water gas shift reaction where the produced carbon monoxide reacts with the water and produce further hydrogen gas. In combination of these two reactions, you can also say overall a direct reforming reaction is this. So the first one is highly endothermic, the second one is slightly exothermic. And overall you could see the numbers, 206, 41, the overall reaction becomes endothermic. Endothermic reaction means it is required. Now the operating parameters, I will not go into detail the equilibrium constant and all this, but just for the sake of simplicity, here you could see what we want is higher methane conversion, right? And you could see higher the temperature, higher is the conversion. And you will see also different graphs for different pressure. That means lower the pressure, higher is the conversion. That's the characteristics of overall reaction. So another parameter here is the steam and methane ratio. So we are putting, as you saw, methane and steam together, right? So another parameter here is the steam to methane ratio. Right? So higher the steam to methane ratio, higher is the conversion. And you could see also the effect together with the temperature. Now the reaction is also enhanced using catalyst. So once again, I will not go into detail. Of course, we will be spending whole day on this. But this is the space velocity of the catalyst. So weight of catalyst divided by flow rate of the reactants. So more catalyst you put in, more conversion you have, right? But here you could see at certain point the conversion doesn't increase so much, right? And the three plots are for different pore sizes, depending on different metal loading on the catalyst, right? So with this graph we know already that that's the amount of catalyst for certain flow rate, this ratio I need, and even if I put further more catalyst, it's not going to help us in conversion, right? So from the plots what we already saw, lower the pressure, higher is the conversion. Now we are already digging into process design. Lower the pressure, higher is the conversion. That means you can use 1 bar operating pressure, right? But problem with lower pressure is also higher volume flow. Right? So can you relate this with your thermodynamic calculation or knowledge? PV equal to nRT, remember? Lower the pressure, higher is the volume. So lower the pressure, operating pressure, higher is the volume flow. And what's the problem with higher volume flow? If you can think about as an engineer, higher the volume flow, bigger is the large vessel is required, large piping is required to have the flow. And with the higher flow rate, if you use smaller piping, what will happen? High pressure drop means higher pumping cost. So if you have lower pressure, high volume flow, either you have to pay for bigger pipe or you have to pay for pumping or compressing. So either capex or opex, capital expenditure or operating expenditure. Right? So once again, lower the pressure. Normally, natural gas is supplied by a pipeline, and you have certain pressure in your pipeline. So for an example, here you have 20 bar pressure in your natural gas pipeline. So is it wise to select operating pressure below 20 bar? Not really, because you already have 20 bar pressure and you will let it down to your operating pressure 5 bar, 6 bar. That's not very wise. So generally, operating pressure is also defined by what's the natural gas pressure we have in the pipeline. Right? Then there is another aspect here. So we are producing from natural gas hydrogen. Right? And you will be specifying what's the hydrogen delivery pressure required. So if it's 20 bar, for an example, right, you will not operate below 20 bar. Otherwise, so let's say if you are operating at 5 bar, you are producing hydrogen at maybe 4 bar with 1 bar pressure drop in your plant, and then you have to compress your hydrogen. So sometimes operating pressure is defined by your conditions you are provided with, by natural gas pressure and hydrogen pressure. Then let's talk about the temperature. We saw from the plot, higher the temperature, higher is the conversion. Right? So definitely you will select higher temperature because you want to have higher per pass conversion. But where is the limit? So higher the temperature, we'll see in coming slides, it's an endothermic reaction. That means you have to supply heat for the reaction, but also to heat up the feed from normal temperature up to your operating temperature. Right? I do not have a plot here for CO product, but looking at these reactions, you could see higher the temperature, higher will be your conversion. But conversion means more hydrogen, but also some byproduct, CO, carbon monoxide byproduct. Right? This reaction has opposite characteristics. That means higher the temperature, higher is the conversion of this one, but this reaction, higher the temperature, lower is the conversion. Right? So that means if we select very high temperature, it will have a lot of CO byproduct. Right? Another problem with high temperature, very high temperature is, if we have very high temperature, operating temperature, we have very high heat demand. Heat up the feed to reaction temperature. So just for sake of simplicity, I can mention here, optimum is somewhere around 850 degrees. At this temperature, we'll have very low unconverted methane. That means we have very high conversion, right, and very low CO byproduct. And that's our target. That's what we want to have. So we talked about two parameters: pressure, temperature. Another important one is steam to feed ratio, steam to methane ratio. You could imagine if we have high steam to feed ratio, means if we are supplying excess steam for the reaction, high will be the conversion and low will be the CO product. But problem with having high steam to feed ratio is, if we have more steam than required, we have to heat up the steam. So additional heat is required, so more energy consumption. Right? So once again, as I mentioned, optimum for pressure 27, temperature somewhere around 850. Similarly, for steam to carbon ratio or feed ratio, optimum is somewhere around 3. Stoichiometrically, somewhere around 2.5 we need, and we supply a little bit excess S3. Catalyst we already saw, space velocity. We saw from the plot that's a certain ratio of catalyst amount versus feed flow rate. So optimum is somewhere around 100 grams per mole per hour of feed rate. So now we already set the optimal operating temperatures or conditions for the reaction system, reactive system. So that's the onion model of process design I was talking about. You guys are familiar. So we start with the reactor system, and we already saw that we do not have full conversion of methane. That means we have some unconverted methane. On top we have some byproducts like carbon monoxide here. Since we supplied excess steam, and we also have unreacted steam left. So what comes out from this reactor or reactive system would be hydrogen, unconverted methane, CO, water or steam, and any other byproduct. Then we look into the heat balance. We already talked about the temperature. We have to supply heat to bring it from feed temperature to the operating temperature. Where are the heat available, waste heat available? So we are talking about 850 as operating temperature. That means the product stream is at 850. What do? We cannot supply hydrogen at 850 degrees. And then finally we will see if we have some heat left in the product stream. So what to do with this heat? Okay, so earlier we already fixed the reaction temperature. We selected as 850. How do we supply heat at such a high temperature? So what are the heat transfer modes you guys are familiar? Sorry, please. Yes? Conduction, convection and radiation, right? And what are the heat transfer medium normally we use to supply heat? Somebody said steam, huh? Steam. And steam can supply heat or energy up to what temperature? Sorry? Maybe up to 300, 400 degree, because at 300 degrees steam pressure is almost 100 bar. So at this high temperature, the only way to transfer heat is via radiation. You burn something and via flame you transfer heat. And can somebody tell me what's the name of this equation? Or maybe the constant? Boltzmann constant, exactly. So here the heat transfer rate is directly proportional to full power of the temperature of two bodies. Difference in temperature of two bodies is full power. Okay, so we already know we supply natural gas and steam, and we already know we are using catalysts at certain space velocity. So normally you take natural gas, burn it, that will create a flame temperature of somewhere around 1800-1900 degrees, and that's good enough to supply heat from the combustion gases to the gases flowing inside the tube. So what happens in the starting, your gases are at 1900 degree, right? And your feed is at, for now we can say 35 degree, ambient temperature, let's say. And you will have very high heat transfer rates in the starting, but as you go along the tube length, what will happen? Your flue gas will get cooler and cooler because it's supplying heat to to your feed stream, right? And your feed stream will start getting hotter and hotter. At certain temperature, reaction will start, right? And it will start to absorb more heat, because we already said it's an endothermic reaction, so a lot of heat is required for the reaction, right? So what it means, ideally or theoretically, I can put a very long tube, right, and cool the gases, the flue gases or the combustion products up to certain temperature, up to 850 degree, right? But what will happen, we saw from this reaction, this equation, that your heat transfer rate is proportional to, or Q by A is proportional to 4th power of T, difference of hot and cold side, right? So once we go along the tube length, your flue gas is cooling down, and slowly your heat transfer rate is also coming down and down. That means you will need a lot of heat transfer area, right? So in the starting, first 1 meter or 2 meter of tube, you will have 70-80% of heat transfer. To have the same heat transfer, you will need maybe 10 times more. So there is an optimum length of the tube, or in other words, there is an optimum flue gas outlet temperature. So you can cool the flue gas maybe up to 1100, 1000 degree, but below this, the heat transfer rate, because the difference, the 1000 degree and 850 degree, that's too low, that you need a lot of heat transfer area, and it's not economical. So last two lines, you could imagine yourself, in the starting you have a very big flame. So generally this flame is 2 meter, 2.5 meter long, right? So first few meter of the tube length, you have very high radiative heat transfer, but as you go below the further the tube length, the majority of heat transfer is taking place via convection, convective heat transfer, right? So flue gas is going this way, feed is going in the tube this way, and the last end of the tube, I actually, to fit in this, on this slide, I just cut it here, but as you go along the tube length, here, majority of heat transfer is via convective, and on top region, it's via radiative heat transfer. So from this, now we'll start preparing the block flow diagram, or the process flow diagram. No? That's the next part of the process design. So you already saw the reactions, right? And we said there will be some unconverted leakage, so that's here, up to 3%. Since we supplied a lot of steam, excess than what is required, so that unconverted steam or unreacted steam is coming here. 45% is our main product, which is hydrogen. You also have byproduct CO, carbon monoxide, and an unwanted product, which is CO2. So once again, for sake of simplicity, we will not go into detailed calculation. We will need another 2-3 hours for that. But that's the typical composition of the product gas, what comes out from the product gas. Now if you apply a simple heat balance between across this reactor system, so the heat out would be, everybody is familiar with this equation, I'm pretty sure, right? Heat transfer forces you already had. So mass flow rate of feed, specific heat of your feed, but from inlet to outlet your feed is converted to product gas. So CP is not only the specific heat of feed, but it's also the specific heat of your product. So somewhere we take the average of feed and product, that's the specific heat, and the temperature difference. So for now we assume that we do not have any preheating of natural gas. So natural gas is coming at 30-35 degree. We have to heat it up to 850 degree, and we have to supply the endothermic. Sorry for this mistake. The reaction endothermic heat actually. And heat in will be the natural gas fuel. So that's natural gas. The same feed what we are tapping out some as fuel. And for combustion you also need air. So that's the air, combustion air. So that's heat out and heat in, right? So we already saw the optimum temperature, right? But in terms of fuel, you could imagine higher the feed temperature, higher will be the fuel consumption, right? And higher the efficiency. With efficiency, I meant what's the flue gas outlet temperature. So when we burn natural gas, temperature here is somewhere 1900 degree, and we said after the reactor system, the flue gas temperature is somewhere around 1000 degree. That means, can somebody say what's the efficiency? Thermal efficiency? 1900 to 1000. So theoretically you can recover heat from 1900 degree up to maybe 40 degree or 30 degree, right? Because your combustion feed was at 30 degree, and you are recovering heat only to 1000. So 1900 minus 1000 divided by 1900, somewhere around 50 degree, 50%, right? So that's the efficiency what we mentioned here. So higher the efficiency, that means if we go lower with the temperature, instead of 1000, if we cool the flue gas to 950, our efficiency will slightly go up. But the downside is you have to pay more for the tube area or the heat transfer area. So it's once again a trade-off between optimization between CapEx and OpEx. If you want to burn less fuel, you have to put in more heat transfer area, which is nothing but CapEx. And only on the combustion side, if you put similar heat balance, so what comes in is natural gas fuel at 30 degree. What combustion air comes in at 30 degree also. What comes out is the flue gas at 1900 degree. And what goes out is the flue gas at 1900 degree. And what else comes in is the LHV of your fuel, right? So that means if I increase the temperature of air, my heat in is increased, right? So if I have hotter air going into the furnace, I will also need less fuel, right? So that's basically a little bit about optimization, trade-off between CapEx, OpEx across the fuel system. We go back to this onion model. We had this reactor system. Separation will come further because we have very hot product stream. So we will first look into the heat recovery system H part of this model. Now we already see product stream is at 850 degree. So you have to supply hydrogen product at ambient temperature, which is maybe 30 degree. Right? So there is a lot of waste heat in the reformed gas or the product gas. We can cool the gas from 850 to 30 degree and recover this heat and use it somewhere within the process, right? So we already saw that heating air and fuel will reduce fuel. So heating air, reduce fuel is what we saw here. And heating feed will also reduce the fuel requirement. That's what we saw here from this MCPTT. So the reaction temperature is 850. If we supply or if we feed the natural gas at high temperature, definitely the heat requirement in the furnace or the reactor will be much lower, right? So what we see here is we have a hot product stream where we can recover heat, and we also have some cold feed stream where if we supply heat, we'll have less operating costs because of less natural gas, right? So what we can do, we can cool the reformed gas and supply heat to natural gas and air, right? So that's typical heat integration, right? Now, what happens So we said we will cool the reformed gas from 850 degree to 30 degree. Right? That means somewhere, whatever heat transfer equipment you will use, you will have somewhere the metal temperature between 850 degree and 30 degree, right? And especially with this kind of product composition, there is a phenomenon called metal dusting corrosion. What happens is this Boulevard reaction, where if you have very high partial pressure of carbon monoxide, it will get converted to carbon dioxide and elemental carbon, right? And what's the problem with this elemental carbon? It can go into your metal structure and it will form metal carbide. That's a form of corrosion. So what we see in only rust, similar metal carbides you will see. And once it starts, it gets very fast corroded. That means you can have leaks, hot spots, which needs to be avoided. What it means? That we have to have the temperature of your equipment handling this composition of the gas never in the range where this metal dusting corrosion is very high. And typically it's very severe between 400 and 750 degrees centigrade. So that means somehow I have to cool the gas from 850 degree to whatever temperature without seeing the metal temperature in this range. Can somebody think about how we can do that? Can you think about cooling a gas suddenly? Sorry? Sudden expansion. Quenching? Somebody knows about quenching? Huh? Quenching, yeah. So what you can do, you simply add water, liquid water, and it will absorb a lot of heat from your gas, and your metal will not see this temperature, right? But what's the downside of quenching? You will cool the gas directly from 850 degree to maybe 150 degree, and all the heat is lost in quenching in water, evaporating water. So you can do quenching and avoid metal dusting, but you will lose all the heat. Suddenly your heat was at 850 degree, very high grade, very high value heat, and you are now converting this to a low grade heat, which is somewhere around 300 degree. So if we avoid, let's say this 400 degree, we want to avoid, we'll simply put water and create a gas from 850 to maybe 300 degrees. But with this, what we are doing, we are degrading the value of heat, degrading the heat what we have in the gas. Yeah, that's another repetition of what we saw here earlier. The severity of this metal dusting corrosion is somewhere around 450, 750 degrees. Right? As you said, there is one option is to quench the gas, right? But with this, we lose a lot of energy and we degrade our available waste heat, right? Another difficulty is once you add water, you are adding a lot of water, you have to remove it all. So your separation system will also become expensive. But fortunately, there is another way. Heat transfer coefficient, individual, overall. So the heat transfer courses you already had. Right? So in convective heat transfer, you know, if you have gas flowing on one side and water boiling on another side, so there is a huge difference in heat transfer coefficient. So the gas side heat transfer coefficient is very low, but if you have boiling surface on another side, heat transfer coefficient is high. What it means? Are you familiar with this temperature profile with film on the hot side, film on the cold side? The temperature drops from bulb to film and across the film. You guys familiar with this?
Yes, such a
So with such a combination, for example, if we have this gas being cooled from 850 to maybe 300 degree, right? And if we have boiling water on the other side, where will be the major temperature drop across hot side to the cold side? Where will be the biggest temperature drop? Where the heat transfer coefficient is high or low? No? So the major temperature drop will be where the heat transfer coefficient is low. Heat transfer coefficient is low means that resistance for heat transfer is high, because resistance is inverse of the heat transfer coefficient, right? So where on the gas side you have very low heat transfer coefficient, your resistance is very high. So the temperature drop, major temperature drop will be on the gas side film, and there will be small temperature drop across the water side film, because it's boiling service on this side. That means instead of quenching, if we start producing steam using this reformed gas or product gas, high carbon monoxide, then in the heat transfer equipment we will not see the metal temperature above 300, 400 degree, right? So for example, if we are generating 220 degree steam here, right? The temperature drop across the water side is very low, maybe let's say 10 degrees, and on the metal surface another 10 degree. My metal on this side will be 260 degree, right? So that's the way you could cool the gas, and your metal will never see temperatures above 300 degree. So that's an intelligent way compared to just quenching the gas. Yeah, that's again the repetition. So you have reformed gas coming in here. Right? Your metal tubes are always cooled with water. With this you can avoid any metal surface with this coming in contact with this high partial pressure, CO temperature, anything about 300 degrees centigrade. So what we are doing here is slowly building this block flow diagram. So first we only had the feed stream coming in, the steam coming in here, right? To produce reformed gas. Now we add another block, which is the boiler, and we already know that we need steam for our reaction. Right? So what we are doing with this new equipment or new block is generating steam and also cooling the gas, right? And also recovering heat. So once we have this steam needed for your reaction need to be generated as well. That needs also energy. So if you can generate within your process, you're already reducing your operating cost, right? So in this one we cool the gas from 850 to 360 degree. As you said, we already generate steam which can be used in the process. Now 360 degrees still a lot of energy left in the gas. Right? What we can do further cool this gas and preheat the feed and air. So another step in heat integration. But we saw the composition of reformed gas. We have some byproduct carbon monoxide, right? And we already talked about this, that the SMR reactions, they are optimally, they have optimum conversion at 850 degree, but the water gas shift reaction, it has optimum temperature, operating temperature of somewhere around 350 or 400, right? That means if we use a certain catalyst, which means if we use a specific catalyst, we can have this reaction. We add another step, and we carry out this reaction to further convert whatever byproduct we had produced from the first step, and enhance our hydrogen production. Right? So we add Another block here, the shift reactor, where as we saw already earlier, the SMR reaction is highly endothermic, but the water gas shift reaction is exothermic, right? It means here the temperature increases from 360 to 420, and you already see we convert whatever carbon monoxide we had, and we reduce the position from 4% to less than 1%. Right? What happens with this? We also increase our hydrogen yield or production. We can even add another step, which is called low temperature shift. So this is medium temperature shift, somewhere around 300 degrees centigrade. We already talked about this. The lower the temperature, higher is the conversion of this shift reaction. We can go even further with the temperature. We cannot have the same. So lower the temperature, higher is the conversion for this water gas shift reaction. But you see, it's exothermic. So as the conversion increases, temperature also increases. So both are going in opposite direction. Right? So what people generally do, if they need very high purity hydrogen and fuel is very expensive, what they normally do, add another step and even bring this carbon monoxide composition from 1% to 100%. But they need to cool the gas from 420 to maybe 250 and then add another low temperature step. So far we talked about the R of the onion model, right, and H of the onion model. We saw even after adding this shift, let's say step, we still have a lot of byproducts, unconverted reactants in our process. So now comes the separation of this onion model. What kind of separation methods we can use if we have to purify a gas stream? Sorry? Somebody said membrane. Right? Good. Yes. Yes. PSA system. PSA system. PSA system. And what's the PSA? Pressure swing absorption. So adsorption is a phenomena of molecules passing through certain structures, certain pore sizes. It also depends on the adsorption forces. And fortunately, hydrogen being the lightest, smallest, very low atomic diameter, molecular diameter, it's very easy to separate hydrogen from other gases using this method. So if you have let's say molecular sieve, some adsorbent material, if you pass through this bed, our product gas, hydrogen will not be absorbed on this way, and other gases will be absorbed. So that means, for example, let's say that's the bed, we have gas coming in, or let's take this example, it's a bed of adsorbents. We pass through our product gas, which has almost 50% hydrogen and other byproducts, right? Through this bed, what will come out here is pure hydrogen, right? But your bed will not last for days or months or whatever, because you are absorbing other gases on your absorbing material. Right? So at certain point, you will not have any space, any pores which can absorb any more gases, right? What you have to do, once again, a trade-off between operating cost and capacity cost. If you make your vessel very big, you can absorb for a longer period of time. Right? But if you make it smaller, within minutes this bed is already charged with your byproduct gases, right? So normally, optimum size of these beds are somewhere around 12 meter, 13 meter height, 3 meter diameter, and they get saturated within not days, hours, within minutes. Right? What it means, you need to have at least 2 beds. So one will be absorbing the gas, and at the same time, once this bed is absorbed, the second bed will be dissolving. And this phenomena, you could imagine, absorption is higher at higher pressure. So if you have high pressure, you can have more absorption. If you have high temperature, you will have less absorption. So we want to have higher pressure during absorption, and we want to have lower pressure during desorption. That's why the name came from PSA, pressure swing absorption. So you swing the pressure, you absorb at higher pressure. Right? Once this is saturated, you simply release the pressure, so gases are removed. But not all the pores are free from the gases. So there is a absorption as well. Even at lower pressures, you will not dissolve all the gases. So what you can do, either increase the temperature of this bag, comes the temperature swing, you have to increase and decrease the temperature, or what you can do is you can pass through pure hydrogen gas or a smooth gas. So whatever, remove the remaining adsorbed impurities, right? So minimum you need two both beds, right? But to have continuous supply of hydrogen, you will need in reality more than 2 beds, because the absorption and desorption times are not same. You can work with 2 beds if you have absorption and desorption time of similar magnitude, right? But normally absorption is, let's say, somewhere around 1 minute, and desorption somewhere around 4 minutes. So that's why you will have more than 2 beds, because of this difference in absorption and desorption time. So these absorption materials or absorbents, they operate optimally at somewhere around 35 degree. What it means, we cool our gas so far from 850 to 360, and we went to shift. Temperature increased because of the exothermic nature of the reaction to 420. It means we need to cool the gas from 420 to 35 degrees. So what we do after shift, we work somewhere around 420. At the PSA inlet, we need to have 35. It means we do cooling here, and we can supply this heat to preheat the gas from 30 degree to 360 degree. What we did with this heat integration, recovered heat from the waste heat product gas before PSA, which was also a requirement for PSA, and thereby increasing temperature of feed gas, which helped us in reducing the fuel consumption, right? Because heat load on the reformer is, or the furnace is reduced. Right? Now, the gas will be cooled somewhere to not from 420 to 30 degree, but in reality up to 150 to 160 degree, right? And you already satisfied all the heat requirement here, right? For the feed. So the remaining heat what will be left will be just rejected to atmosphere via cooling water and air cooling, right? So that's the U part of your overall onion process design. So we already looked at the heat recovery on the process side, the product gas, but we saw that our flue gas is also at 1000 degree. And there's a lot of waste heat available in flue gas. We saw that economically we selected 1000 degree based on capex opex. Higher the temperature, bigger is this temperature is, lower is the heat transfer area required, but on the other side we need more fuel. Flue gas, normally we can recover heat from 1000 degree to 150 degree. Do we have any consumer or any other process stream which need heat? So we heated the gas up to 360 degree so far. We saw it. You saw it here, right? And where this 360 degree came from? Because we have the hot stream at 420 degree, right? So we cannot heat our feed gas above 420 actually. But there is a optimum temperature approach. Temperature difference between hot stream and cold stream. So in this case, it's somewhere around 60 degree. So we can heat the stream up to 360 degree because our product gas is at 420 degree here, right? But what we can do, we can heat it further to 650 or even higher using hot flue gases. Right? We already know, we repeated that several times, that higher the feed temperature, lower is the fuel consumption because heat demand is low. So we heat the gases from 360 to 650 using flue gas. We can generate further steam because we saw so far we are not generating enough steam within the process. We do generate in this boiler, but we still have some steam requirement from external sources, right? So flue gas can be used to generate steam, right? And we can also preheat the air. We already talked about it. Hotter the air temperature, lower is the fuel demand. So further optimizing it, what we can do, we can preheat the air also from 30 to 450. Now if you look at the temperatures here, it's 450. So gas is being cooled from, let's say if I have a plot here, 1000 to 150 degree, and we have a temperature cross somewhere here. Air is to 450 and the steam is generated and superheated to 350. So it's better to split the air preheating into two steps to have optimum use of your heat. What we do, we split the air preheating into two steps. First, increase the temperature from 30 to 250, then generate steam, and then this 250 air, what comes out here, goes in here, comes out at 450. So what we are doing here is having a regular temperature profile. You could see here, so 30 degree, 250 degree, another stream 350, then 450, and then 600. So you always use your heat at the optimum temperatures. Right? So that's how the overall block flow diagram looks like. We have natural gas coming at 30 degree. We preheat it to 360 using product gas. Further to 650 using flue gas. 650 degree natural gas together with steam goes to the reactor, right? And when we talked about steam generation here, when we had steam generated here, we had steam requirement from external sources. But once we started to generate steam here, suddenly we have excess steam generated, more than required in the reactor system. And that's why our block diagram now changed from this side to this side, from this side to this side, right? So we had this R reactive system here, H heat integration on here, separation here, and final cooling from 150 to 30 degrees, that's utility U here. So that's how we complete our onion model for the process design. Right? And that's how the overall block flow diagram looks like here. So this is just the block diagram just to show how the flows are here and there, but in reality it looks something like this. You have the natural gas coming in. You need some heat treatment, which I will skip just for the sake of simplicity. And that's how your furnace looks like. You have the natural gas fuel together with air, burn, catalyst filled in the tube, feed stream coming in here. You could see natural gas coming in, preheated, pre-treatment, further preheated, and then entering the tube at 650. Hot gas coming out 850. There is steam generation here. That's the steam drum, the shift, what we also saw in our block diagram. Further cooling, preheating the feed, right? And final cooling, PSA system, and then you have your hydrogen product. Right? questions so far? Interesting? Not interesting? Sorry?
CO and CO2.
So what happened? What happened? Yeah, good question. Good question. So what happens is you separate your pure hydrogen here, and generally you have 90% recovery of your hydrogen, because we saw during the desorption step, you need pure hydrogen to remove your gases which are absorbed, right? So you will have somewhere around 89-90% recovery here, and all the CO, CO2, a little bit of water, they all ended up here in this tame gas. This is called tame gas. So during the desorption step, we supply hydrogen. First of all, it's depressurized, right? You don't supply any sweep gas. So the gases are dissolved automatically, and all these components are ended up here. All are in this stream, right? Since this stream contains a lot of carbon monoxide, some unconverted methane, some hydrogen as well, because we use soup gas, pure hydrogen and soup gas, it has some fuel value. So what we do, we use this as fuel. So here you could see natural gas with feed, and this was a fuel stream. And if we have this byproduct stream which has some fuel value, we add this with the fuel. So they all this CO, remaining CH4, hydrogen, they all are burned in the furnace and end up here in this process. That was a question, huh?
What if we use pyrolysis instead of recording? Because we don't have any carbon byproducts in this. Carbon dioxide or monoxide byproducts.
Yes, that's a new, we'll see in the next presentation what are other methods of producing hydrogen. So pyrolysis is one. It's still in very early stages. We'll see in detail on this process. So far we talked about the process design, the temperatures, operating condition, and heat integration, right? Separation. So that's all the technical stuff. Now we go from process design to a little bit on economics. So once again, just for sake of simplicity, I already put the specific natural gas requirement somewhere around 13 to 15 megajoule per normative cube for the hydrogen. Right. Now if you consider natural gas price somewhere around 30 euro per megawatt hour, if you do a simple maths, that's in euros per megajoule, right? That ends up at 1.16 euros per kg of hydrogen. Within your plant, you don't use only natural gas. Here you see in the block flow diagram, basically you are using natural gas and some electricity, generating hydrogen product. We already talked about this. We have excess steam production, so we can sell this steam also. So we don't see here, we are generating steam. When you generate steam, you also have some blowdowns, some makeup dam water requirement. So there are some other operating expenses. It's not just natural gas, but natural gas is the major operating expense in a SMR process, right? So let's assume, once again, sake of simplicity, 10% for other OPEX. Right? We end up at 1.36. But to do all this stuff, we also need to buy and install this plant. It's a capital expenditure. Once again, let's simplify it. 15% of your total cost is for capex, and the remaining 85 for opex. Means hydrogen price somewhere around 1.5 euro per kg. I think that's, if you convert it into rupees, that's a similar price is what we have here in India using SMR process. So we slightly talked about this steam co-production. So let's look at it in a little bit detail. So operating parameters we already defined, and what we define for this example, we end up with steam co-production, right? So high reforming T or reaction temperature, that means we need to fire more, burn more fuel. What it means, we have more waste heat in the flue gas and more steam co-production. Right? Similarly, high reaction temperature, more heat in the process side. Right? The forming temperature is high, that means product gases are not at 850, it's 950, and in the boiler you generate more steam. Once again, high, but the other side, so first two are towards more steam production, right? But if you have higher temperature, we also have higher conversion. Right? Higher conversion means we'll have less throughput for the same amount of hydrogen production, and we'll have less steam. Also, higher temperature, reaction temperature, more conversion, less process and waste process side flow, because for the same hydrogen throughput, you also need less feed, right? So the flows are also lower. It means once again less steam. Another parameter, high steam to feed ratio. That means more conversion. More conversion means less wasted in the process. Once again, less steam. But on the other side, if you have higher steam to carbon ratio, what will happen? You have to fire more because you are flowing to the whole plant a lot of additional steam. That will generate more steam. So higher steam to feed ratio has two effects, and both of these two effects are in the opposite direction. So one will have less steam, one will have higher steam. So what I want to say here on this slide is, it's a complex, complicated combination of different parameters, and for optimization you need to select best combination of all this. Right? But the air preheat has only in one direction. Higher the air preheat temperature, less waste heat in the flue gas and less steam. And this high air preheat temperature will have biggest effect on your steam co-production, because we saw in this waste heat recovery part, if you preheat your air higher, you will generate less steam because you have same amount of energy left in your flue gas. So if you increase these two, this one will go down. So air preheat temperature has the biggest effect on the steam co-production. We said already that with these parameters will produce steam as byproduct, right? And can sell this steam. And how do you value your steam? Huh? So we already said natural gas price somewhere around 30 euro per megawatt hour, and LHV of natural gas, for example, is around 47, right? So natural gas value in megajoule, and let's assume we are generating steam at 40 bar, superheating it to 350 degree. That has a heat enthalpy of somewhere around 3200 kilojoule per kg or megajoule per ton. So if we assign 1-to-1 value in natural gas to steam, your steam price would be 27 euros per ton, right? But we know there is an efficiency of natural gas to steam conversion, right? Somewhere around 90%. The steam price will be 30 euro per ton. Right? And once again, we saw from previous slide, the capex simplicity. We assume, let's say, 10% here, 10% of your total cost is capex. So as my steam price will be 33 euro per ton for assuming 1-to-1 value, right? And generally, so we co-produce steam with hydrogen, right? And how much it is? Generally, for these parameters, what we selected is somewhere around 0.3 kg steam per 1 meter cube of hydrogen. And if you convert non-meter cube to kilojoule, you end up with 3.3 kg steam per kg hydrogen. What we are trying to do here is establishing 1.5 euro per kg was our hydrogen price. How much money we can get from steam and reduce our production cost of hydrogen. Now we assume in the previous slide the steam value as 1-to-1, but it rarely happens that you get the same value of your steam Generally, steam value is somewhere between 30% to 120%. You never get full value of your steam or the energy content what you have in your steam. So generally you get less than 100%, but at some locations where imagine you have a plant, your plant, and they suddenly need some steam, right? They don't want to install a boiler or a steam generation system within their limits or within their plant, and they come to you and say, you have some excess steam, can you supply steam to us? And there, in such scenarios, you can have a little bit higher value of the steam dispute, but it rarely happens. It's always less than 100%. So if I translate 3.3, right, and it becomes 10 euro to 40 euro per ton of steel. So we saw in the previous slide is if for 1-to-1 it's somewhere around 33 euro per ton, but if I get only 30%, it's only 10 euro per ton of steel. So my hydrogen price will go down either from 0.03 or 0.13, so 1.5 reduced to 1.47 or 1.37. So as I said earlier, optimization of operating parameters is really based on price cost data. What's the natural gas price? What's the hydrogen price they will pay? And what are the cost of utility? So far we talked about this reactor system, only reactor tubes, but that's how it looks generally, somewhere around 18 meter high. You will have tubes here somewhere around 12 meter. So there are different design of these reformers, but most of them have tube length somewhere around 12 meter, and you supply your feed stream from top. Most of these systems are top fire, means you are firing from top, feed also coming from top. Catalyst is generally catalyst, nickel base, loaded on aluminum oxide. There are several licenses for designing such plants. So apart from steam methane reforming, you can also have partial oxidation. It will also generate syngas, but partial oxidation generally has higher operating temperature. That means your CO content is high. So SMR is best suited for pure hydrogen production, but in many cases you need combination of CO and H2. One example is methanol. So methanol production you need carbon monoxide and hydrogen in a certain ratio. Then you sometimes supply SMR and ATR combination or POX. So there are several other methods of producing hydrogen. But today we'll limit our discussion only on the SMR. Yeah, with this I rest my case and conclude.